Hey, hello again, Ace. This is DP here for the Displaced Ace. This week we're talking about accidents and mishaps and the causation involving human factors in unmanned systems. So a couple of things that are related to accident causation are hazards and risks, and those two are often used interchangeably, sometimes incorrectly. So the difference between a hazard and a risk is a hazard is a thing. It could be a physical object or lack thereof, an environment, variable, or a state of being. So it's just something that exists that could pose danger basically to whatever your mission is, or in this case, aviation operations. Whereas a risk is the dangerous situation that arises from the hazards that are present in the environment or the area you're operating. And a risk also requires immediate attention or reaction from the pilot to avoid a consequence. So, to give you an example, a hazard could be a mountain in the area you're going to fly. The risk is operating close to that mountain. So, you fly too close to that mountain. If you don't react properly to that risk and control it, you may impact the mountain, resulting in the consequence of loss of life or aircraft. So, that's kind of a simple breakdown of how those terms are differentiated. One of the biggest or most risky situations for UAS operations is beyond visual line of sight, or BVLOS. You'll see it abbreviated that way in some cases. So operating beyond the area where the pilot is able to see it with his human eyes. That's usually done through cameras and onboard systems, satellite links, or some sort of RF frequency to operate the aircraft at that distance. Ways to mitigate the risk, which would include like air-to-air collisions, air-to-terrain or CFIT in that case, beyond line of sight when you're not there physically in the aircraft to observe all these things. First thing would be anti-collision lighting, so make sure your navs and strobes are on, just like you would in a manned aircraft. And that way, other aircraft in the area can see you operating and avoid you as necessary if you don't have any sense and avoid type systems on your aircraft. Some aircraft are capable of carrying a radar or other cameras or payloads for stereo vision that would be able to potentially sense and detect or visually pick up other air traffic on the cameras and avoid it as necessary. Other things you can do to mitigate the risks of beyond visual line of sight operations are have a pre-planned routing, which usually is required if you're operating in the NAS. So for your FAA COA, you're going to iron out and file that pre-planned routing with the FAA as well as altitudes, and then have a contingency plan. So if the aircraft goes lost link at a certain point, or you're no longer able to have control of the aircraft as the pilot, what's the pre-planned routing, altitude changes? Is it going to loiter somewhere? Is there a pre-planned ditch point basically if you lose total thrust in the aircraft and you have to crash it into the ground, a controlled crash of some sort? Is there a pre-planned place that mitigates any sort of risk to property or personnel on the ground? Having all that mission planning done ahead of time and knowing what you're going to do in those contingencies really mitigates a lot of the risks of beyond line of sight operations. Another option, which is pretty popular, is manned chase planes. So you can have another aircraft fly along with it and monitor its operations so that if you do lose control of the aircraft as far as manual inputs with the command link, then the other aircraft can monitor its operations as well as radio to any ATC in the area, let them know what's going on with the aircraft and what the pre-planned routing will be for its lost link procedures. Finally, I would advise having multiple communication methods with ATC, whether that's through a chase plan on their radios, having your own line of sight radios on the aircraft with the controlling agency, then having a phone number readily available in your control station for the controlling agency, and then if it is available, some sort of digital text form of communication with the controlling agency if that's available for your operations. All those can give you different ways to reach back in the event that you do go lost link or have some sort of abnormal operations while the aircraft is beyond line of sight operations. And finally, you can also use your typical Mode C or Mode 3 squawks to also notify ATC and other aircraft of what's going on. There are certain codes in different areas of operation that you can squawk in your Mode 3 that will give the other aircraft in the area, as well as anybody like ATC with a scope, to see what you're squawking, and they'll know you're an emergency aircraft or a lost link aircraft. And finally, I want to talk a little bit about how human factors have contributed to the UAS mishap and accident rates. There's been a lot of studies thrown out back and forth, depending on how far back you go, where unmanned aircraft were highlighted as had way higher accident rates in comparison to manned counterparts. That's been debated so far, and that may not be completely accurate. There are some studies, and I'll list them in the references below, but um, initially you are going to have higher mishap rates as the platform is developing and pioneering new technologies, and that's a lot of what was going on with unmanned aircraft, especially in the military for the MQ-1, MQ-9, which are usually highlighted as those higher mishap rates. You had premature technologies that were rapidly fielded basically, and just hadn't had the flight hours and experience or crew training involved to evolve that technology and design it better to eliminate some of those human factors. So initially you had very high mishap rates with some of the unmanned aircraft. That's created kind of a stigma that's not necessarily true across the long term as the technology evolves and as it gets to a lifespan that's comparable to other manned aircraft. I think you'll see those mishap rates actually even out or be very equitable to manned aircraft, which is what a lot of the studies indicate. Um, One of those studies in particular highlights the interrelatedness of automation, HMI, and crew errors. So just looking at how the cockpits were designed, again, that technology wasn't really mature yet, so things were kind of strapped on and put in different places in the cockpit that wasn't really ergonomic or well designed, which created some mishap errors. Other things and human factors related to the mishap rates. In particular, there's a couple case studies. One involving MQ-1, where the MQ-1 was on station and was warned about weather coming into the area, possible thunderstorms and light icing. Then they were tasked to support a TIC or troops in contact, so an immediate danger situation for troops on the ground, elected to stay another 30 minutes despite the weather, and that ended up in the aircraft being struck by lightning and falling uncontrolled to the ground and crashing. So being not in the aircraft can change your decision making on whether that was a good or bad decision. Um, some would definitely argue that protecting the lives of the troops on the ground was worth the loss of the unmanned aircraft, but because the pilot doesn't have that personal risk of being in the aircraft, that can change the decision making, and some of those human factors do contribute to accidents where additional risk is taken that maybe wasn't necessarily warranted in some cases because there is no risk to the pilot's life itself. Another case study shows an MQ-9 right after it's transitioned. Was called the gaining handover process, where the aircraft controls transition from the takeoff crew to a mission control crew. And in that case, the mission control crew had an improper autopilot or altitude command setting, and it caused the aircraft to climb at the time they handed off control. The mishap crew didn't realize that they had that setting in and couldn't figure out why the aircraft was climbing. The pilot elected to take full manual control of the aircraft, which takes off a lot of the safety features for the autopilot, including the stall protect features. Eventually, he did stall the aircraft. It did enter a spin and then crashed about 2 minutes after he had gained control initially from the handoff. So that's a case where being in an unmanned system or a remotely piloted vehicle, that lack of sensory cues, which is highlighted across a lot of works looking at UAS accidents and mishaps, so he didn't feel the aircraft decelerating or in the high pitch attitude or anything like that. The only thing he had was visual cues on a screen and some audible warnings indicating that those high AOA and stall conditions were being approached. And the lack of sensory cues physically on the body in that case resulted in a stall and a spin out of control. So there's some things to be aware of when you're operating not only an unmanned system or remotely piloted, but also looking at the contingencies and potential risks for beyond line of sight operations.